In part 3 of work, we'll do some calculations now, applying our definition from video 2. Calculate the work done by the 5 Newton force as the block is moved 5 meters up the inclined plane with a 40-degree inclination as shown below. Remember, to calculate work, you must first identify the force. Now, what a lot of people do is they draw what are called work diagrams. So here's the block, and I have a displacement vector here, and in this case that displacement vector is going to be 5 meters up that incline. And I also have, let me change colors here, a force applied to the block, and that force is applied over here, and it's 5 newtons. And then there's an angle here, that angle theta, which is 40 degrees. Now this is not a free body diagram because I put a displacement on here, not just forces. It's designed as a work diagram designed to let me compute dot products. Alright, now let's first do it in the polar form, which is the most convenient for this problem because I've got angles and I have magnitudes. So this is how I would do it if it was me. I'm looking for F dot delta R, which is F delta R times the cosine of theta. That would be 5 newtons. The displacement is 5 meters, and the cosine of the angle between the two is 40 degrees. So that means that F dot delta R is approximately 19.2 joules. Okay, and this is the work by the force F. Now, it's a positive number. That means that F is attempting to speed up the block. Attempting to speed up the block as WF is greater than 0. We'll quantify exactly how that is later when we develop the concept of kinetic energy. That is energy of motion. Now, I also could do this in Cartesian form, but it wouldn't make a lot of sense because I don't have these vectors easy and in Cartesian form, but I'm going to do it just to show you that it could be done. So if I was trying to do this in Cartesian form, I would first need to write F in Cartesian. That's not hard. That's just 5 newtons I hat. And second, I would need to write delta R in Cartesian. And delta R in Cartesian is 5 meters times the cosine of 40 degrees I hat plus 5 meters sine 40 degrees J hat. That says that delta R is approximately 3.83 meters I hat and 3.21 meters J hat. How did I get that? Let me go back up and look at, you have this vector delta R, and all I'm doing is there's X, there's Y, there's theta. I simply am breaking it into its components. Alright, so there's delta R Y component, and that's delta R the X component. To find this side, the X part, I used the cosine because it was the adjacent side of the triangle. And for this side, I used the sine because it was the opposite side. And that's how come I got those two. Now, to go ahead and apply the dot product, remind you of the following, that the dot product is then going to be the X component of the force times delta x plus the y component times the part of the displacement along y. So W would be equal to 5 newtons times 3.83 meters plus 0 newtons in the y times 3.21 meters. And when you plug that in, you find that it's 19.2 joules, just as you did with the polar form. Now the polar form by far makes sense here because you have the links here, F and delta R, 5 meters, 5 newtons, and you knew the angle. But if the vectors had been written in Cartesian form, if this is what you've been given, then this form would have made more sense. By the way, just so you make sure you know, this is delta x, the displacement in x, and this was the displacement in y. Some other important things about work. Work is a scalar. As you saw here, I'm adding numbers. I'm not adding vectors anymore. And that means that if you have many forces in a problem, as you usually do, you may want to compute the net work. It's this that's going to determine whether the object actually speeds up or slows down. So here's the work by force 1. Then this would be the work by force 2. And so on and so forth. This is better than summing up the vectors first vectorially and then computing the displacement dotted into that force. And the reason is that some of the forces may do no work, and therefore their terms may be 0. This is basically nothing more than just adding up scalars. When you add up scalars, think of the work like money. You could have money in your bank account, you could have money in your savings account, you could have people adding money, you could have people withdrawing money. To calculate the net change of your money and how much you have, you need to count how much money is in your checking, how much money is in your saving. Did anybody take any withdrawals? That'd be a negative W. Did anybody make any deposits? That'd be a positive W. You need to add up all of that to find the total amount of money you have. An example of applying that, let's compute on this hot dog the work done as you slide this hot dog in this direction, D, where that distance is 0.35 meters, and you have many different forces. You have force 1, force 2, force 3, and we have the normal force here, and we have the weight. And I want to calculate the work done in each one of those cases. So F1, let's calculate the force 1's case. Okay, for force 1, work 1 would be equal to F1 dotted into our displacement vector D, which would be force 1 times the distance we pushed it times the cosine of the angle between force 1 and theta. W1 would be, I'm told that the force is 5 newtons. I'm told the distance is 0.35 meters. And in this case, the angle between this vector and that vector is 0. Plug that in and I get 1.75 joules. What about for force 2? W2 would be equal to F.D, F2.D, which would be F2D cosine theta 2. This would be equal to, force 2 is 1 newton, distance is 0.35 meters. But this time, this vector points that away. That vector points in the opposite direction. This angle is 180 degrees. So cosine 180. Plug that, I get minus 0.35 joules. Force 3. Work 3. is F3 cosine theta 3, and that would be 4 newtons times 0.35 meters times the cosine of 60 degrees. And when I plug that in, I got that it was 0.7 joules. What about the weight? Well, the work by the weight would be equal to mg times d times the cosine of the angle, but the angle is 90 degrees. So that's 0 joules, because the cosine of 0 is 0. And the normal force? The work by the normal is the normal times d times the cosine of 90 degrees. And it also does no work. And I don't even have to compute either the weight nor the normal force, since they do no work. To do the total, we simply add them up. 1.75 joules plus minus 0.35 joules plus 0.7 joules plus 0 joules plus 0 joules, and you plug that in and you get 2.1 joules. What does that tell us? The object is speeding up as W total greater than 0 joules. Some of the forces, like F2, are trying to slow it down, but more of the forces are speeding it up, creating a total in positive work. Alright, that covers this video. We'll go on to more topics in the next video.